Okay, thank you, Catherine. Good morning, everybody. Thank you for joining this webinar. Just a comment about what I'm going to be using in this short talk to you. It's going to be relatively short. Most of the research that I will refer to is done by experts, present and past. And in fact, most of the reports that we read, not only the one that I'm going to be using about theories in education, are secondary sources, the results of others in the field itself. But I usually, you may have heard me saying that before, I usually work with the thinking that I don't need to know everything, I just need to know where to find it when I need it. And this is not my say, this is Einstein. And if Einstein does that, well, why don't I? I just want to use a statement to confirm this one that Newton said. And he said that if I have seen further, it is by standing on the shoulders of giants. And that means that if he had been able to discover more about the universe than others, then it was because he was working in the light of discoveries made by scientists, either in his own time or an earlier. Now for our topic, as you know, we're in a world where machines are actually programmed to do mathematics. It is natural to wonder, what do mathematicians do? And applied to us as teachers, this translates into, when the students use technology to do the mathematics, then what do the teachers actually still have to do? Don't worry, we still have our jobs. Okay. Let me see that. In a world that is rich with changes, we must use what we learned from the past and make the most of the future. Our historical role as educators has not really changed, but the emphasis is now evidently on selection and interpretation rather than manipulation and procedures. As teachers, we feel the necessity for a major shift in the instructional methods we employ to impart mathematical knowledge to our students. The Pearson's MYP series, this is not advertisement, but I just need to mention it because that's what got me involved in this, in the MYP work. So the Pearson's MYP series, which I helped with, has its philosophy centered on three key ideas. Delivery of mathematical concept follows recent research on how students learn. And the main thing is that the students need to explore, discover new ideas before being taught. That doesn't mean that we don't tell them. That means that they need to explore it themselves. And the second idea is that the problem solving is central in learning mathematics. And that would be, as you see here, I put a definition, something for the Pierre Van Hele. And I hope that some of you may have read something about the Van Hele husband and wife. And he said that a definition of a concept is only possible if one already knows to some extent the thing that is to be defined. Of course, this is not advanced math where you just start from scratch saying, let X be something and Y be something else, and then you come up with a theorem. So students need to know what it is that you're talking about so that when you talk about it, it becomes a little bit more familiar. The third idea that we have would be that the cooperative learning is sorry, I just went a little bit. Cooperative group work in the classroom is very helpful tool in changing the students from passive receivers of information into partners in the learning process. Now, this does not mean that with these three ideas that they are separate methods that follow at different times. In fact, the process is a combination of all of them, one to support the other. And the approach that we took would be that the students need first to explore so that they can actually get familiar with what we are going to be introducing them to. They'll be encouraged to become good problem solvers by following problem-solving rubrics. And we suggest using the group work in order to enable the students to communicate what they are discovering, what they're exploring, and how they are solving their problems. Math in our time is not only doing the math itself, etc., but communicating what we solve is a very basic part of the whole process. Let's start with the thing that you face almost every day. What would prevent students from solving mathematical problems? Unfortunately, I can't ask you that question and get your answers, but I'll suggest some answers. There may be something about the wording that they don't understand. They may not see how to get started. There may be no obvious strategy for them to use. They may not know the right part of the mathematics to use. They may believe that teacher wants a particular method and they cannot guess what it is. They may know the strategy and the mathematics, but may not be using them correctly, or may not be able to see how to put them together to come up with a solution. I'm sure those of you who are familiar with him and many other mathematicians would agree that the father of problem solving in school mathematics or was the 20th century mathematician Georg Polya. Polya taught at Stanford in the 1940s and wrote the book How to Solve It, a New Aspect of Mathematical Method, a general guide for solving both mathematical and non-mathematical problems. And here, before I refer you to references afterwards, when it comes to problem solving, and you haven't read the How to Solve It book, it is a good idea to start. Starting late, better than never. I did not start, or I did not really read it till later in my career. About half the way in my career, somebody suggested it to me or asked me whether I read it or not. And I was more or less embarrassed to say no. It is a good idea that we look at the studies or at the suggestions that Polya brought forward. He suggested that maths should be shown as being able to solve problems. So in other words, he put math and problem solving hand in hand. His book includes his famous 4-step problem solving heuristic, and he suggested that by displacing mathematical thinking as a way to uncover unknowns, it becomes more engaging for the students. And there were a lot of concepts about problem solving. One, actually, historically, the starting one would be that problem solving as a context, which is based on the idea that problem solving is a method used to accomplish something else, justification, recreation, etc. Or problem solving as a skill, where with the drill, you solve routine problems and you become better at it. And the last, which Polya actually contributed a lot to, is that problem solving as an art. anyway, I'll leave it for you to really read about problem solving from Polya, so that you just get a better view of it. I hope that you have already. So a quick review, perhaps here we can say that it is a, one second, that we discussed the problem solving first, mentioning the exploration and the group work as ways of achieving our goal. In this way, I will be mentioning what Polya meant by his 4 steps of the problem solving. And at the same time, I'll just give some examples of how to apply it in the classroom. Any time we have the chance, whether in our teaching or in any other aspect of the classwork, etc., students should be encouraged to follow the heuristics so that they can get used to it and it becomes part of their rubric of every day. Given a problem, you follow these steps just to be on the safe side so that you can achieve your objective in the end. Many times, I think, if you try to recall how your students work, if they don't follow a methodical way of problem solving, is that you give a problem for students to solve. I'm not saying really this is theoretical. This is my observation in my own teaching when I did it in class. They immediately start working. And they immediately or shortly after that, they give up. I cannot do it. Show me how, etc. And the thing is that they always start at the wrong step that is being suggested. Now let's go through what Polya suggested. The first thing, which is of course obvious, would be to understand the problem. Where should I start? Start with the statement of the problem. What can I do? Visualize the problem as a whole, as clearly, as vividly as you can. What can I gain by doing so? You should understand the problem, familiarize yourself with it, impress its purpose on your mind. This is what Polya says. Naturally, students will not be able to solve problems unless they can first understand it. This process requires not only knowing what they have to find, but also key pieces of information that need to be put together. Of course, they can highlight things. They can, if they are working in groups, therefore they can explain it to each other. And that would be a good thing that you encourage in class, is that when you put them in groups and they are solving problems, have them pair up within the group itself. The group doesn't have to be only 2 people, it can be 4, etc. That would be the ideal that we can really expect, and have them in pairs explain it to each other so that they could really see that they understand it. And when you tell what you understand to somebody else, you have another opinion. If that person does not understand it, this means that there is something missing that you're not getting, and it may not lead you towards the end. So read the problem and reread it, etc. Can you determine what you're looking for? What facts are given? Is the given information sufficient to solve the problem? Etc., etc., etc. And as I think Einstein said it, if you can't explain it simply, then you don't understand it well enough. And if that is the case, then if you don't understand it, you may not be able to get it. Now, in the diagram that I'm showing, I hope that I'm still showing it, I think so. You see 2 arrows. The green arrows would be the poly a suggestion, but realistically speaking, it's not a one-way process, etc., etc. And that's why what I draw here in red, this means that you can actually go back. If you understood the problem correctly, or you think, or you thought you understood the problem correctly, when it comes to developing a plan, you may discover that you didn't understand it good enough. Therefore, you can go back and check your understanding for it. This is what I mean by the red ones. Now, the making a plan or devising a plan, which in our series we call it Make a Plan, the map. It is sometimes it may even require guessing while you're trying to make your plan, etc. You may end up trying to guess where the result is going to be. There is nothing wrong with guessing. Of course, we sometimes may end up saying, no, 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 don't guess. No, that is not true. Guessing is fine. You can, if your guess is not correct, therefore you can, while carrying out your plan, as we will see in the third step, you may discover that this guess was incorrect, and then you can go back and correct it. So mistakes are all possible. They're an outcome of this process, and actually you should really make use of them. And this is the new theory of brain, how the brain works. And this is what Joe Bowler had advocated and publicized. Actually, she was not the one who discovered it, but she took the reports and made use of them in terms of math. This is another author that I would recommend that you look at her work. Have you ever seen this problem before? Can you make a simpler version of it if it's too difficult? Have you seen a related problem, etc.? All these things should come to mind when you are developing a plan. I could mention that in my teaching, especially, no, not especially, actually this can happen everywhere. The students who end up giving up quickly afterwards will not really be developing a plan. What they would be doing would be just doing some symbolic manipulation, or in other words, they would be carrying a plan that they did not really make and getting stuck immediately. And as Newton says, no great discovery was ever made without a guess. So guessing would not be a bad idea. There are many strategies which you can also look up for problem solving, work backwards, divide the problem into sub-goals, etc. All these steps could be done, and you should really encourage your students to learn that having difficulties in solving a problem would not be a bad idea. Here, I just want to mention something, is that many of us, when faced with a question that is posed by a student, will immediately jump to saying, here is how, directly. As I said, in the middle of my career, etc., I changed that. I used to kind of feel very belittled when I don't know an answer to something, etc., and therefore I should give an answer. No, I don't want to say correct, because we may disagree on that. An alternative way would be, if you're asked a question back. And here, that brings another difficulty for you. If you are not all unified in your department in problem-solving approach, then you may have a little bit of problems with the parents, because if you end up answering a question by another question and the students don't like it, they go and complain to mom and dad, and then they'll ask the school to transfer their kids from your class to the class of a colleague that gives answers all the time, etc. Have I met that? 100 times, if I don't want to say more than that. But insisting on the method and convincing students that they will benefit from it afterwards would pay off. I promise. The third step that Polya suggests would be, after establishing the plan and making sure that it works, etc., is to work out the plan. This is where, as I mentioned earlier, most of the students start. Starting after making the plan would be a good idea. Starting before making the plan may not be a good idea. While working on your plan, solving the problem that you have at hand and so on, you may discover that there are parts of the plan that indicate that you haven't understood what is really required from it. And if that's the case, therefore, you better go back, and this is what I mean by the red arrow here, and try to understand what is confusing and so on. And after that step, you either go back to finishing the carrying out of the plan, or you go back and adjust your plan and then come back to working it out. And of course, there's a lot of work here, and we can, I mean, I like quoting important people, and like when Newton says, if I've ever made any valuable discovery, it has been due more to patient attention than to any other talent. And as Einstein said it also, it's not that I'm smart, it's just that I stay with problems longer. So while working on your plan, keep an accurate record so that you can recheck it afterwards. After finishing what you think the problem is, etc., looking back is something that many students, even fairly good students, when they have obtained the solution of the problem and written down neatly the argument, shut their books and look for something else. Doing so, they miss an important and instructive phase of the work. A good teacher should understand and impress on his or her students the view that no problem whatever is completely exhausted. They have to try to look back. One obvious thing is that after you finish doing a problem, try to see by looking back at whether your answer makes sense or does not make sense. I mean, I don't know, if you teach probability and so on, so many times you end up having answers that are more than 100% or a negative number for probability, etc. This means that the students did really not look back at whether the answer made sense or not. Probability is one example. Trig, when somebody gets a sign of 1.2, etc., that means that something went wrong in carrying out the plan. But this is something that you hope for, and I'm not sure that it is always practical to expect it from students and so on, is that try to see if the result that you got can be extended. And that is for those students that are a little bit more inclined to like the math more than the others. I can tell a story that happened to me personally in one of my classes. I have seen, and I'm sure that many of you have seen that problem. The problem is you're given a parabola y equals ax squared plus bx plus c, and you're asked to see how the parabola behaves as you change the parameters. What happens if c changes? That's obvious. It's a vertical move. What happens if b changes, and what happens if a changes, and so on. The article, of course, gave the answer. I thought, no, I don't know whether I'll give you the answer or not. No, let you figure it out. I'll just give a hint, is that if A or if B is changed while the other parameters are fixed, then the locus of the vertex of the parabola would be another parabola. You can find it. After finishing this investigation with my students and so on, I looked back and I said, what about if it's not a parabola? What if it's a cubic function? And worked on it, discovered some pattern. The question, of course, went on, what happens if it is a polynomial of degree 4? Well, also something that is interesting. In the end, it was possible to generalize it. Unfortunately, to me, somebody else may have discovered similar result before, so didn't achieve anything to publish. Anyone that is interested in that one, you can send me an email and I'll send you the result. This is for the problem solving theoretically. I just want to give you a couple of examples. By the way, anything that I'm saying now, etc., you could read in full when you get the teacher guide that comes with each of our books. In the introduction, I mentioned almost everything that is in this session. Let's take a problem and see how it is applied. Okay. In one of the books here, it says, construct a parallelogram with the lengths of the two of its sides equal to the lengths of the segments given below. The segments are G and H. I was going to say B. Needless to say that in construction problems, the best thing is draw a picture at the beginning, whether it is correct or it's not correct, just to approximate what you are looking for. And understanding the problem would be translated by drawing this picture, as you have seen here, even though it's in a textbook, but we made sure that it really is a hand-drawn picture. So if you want them to be the same as G and H, therefore this is a parallelogram with G and H. By studying it a little bit further, you notice that for the parallelogram, the opposite sides should be congruent. And since there is no other condition, I think you may discover that you really don't have a unique solution for this thing, but you can still construct it with the conditions that are given to you, that the lengths that are there. Making a plan is connected to this one, and I'm sure that you can see it. To satisfy the given condition, we need to copy the line segments. Students should be familiar to copying line segments and so on. This is a construction using the compass and straight edge only. So copying it would require that the student takes the length G with the compass, drawing a line with the straight edge, not a ruler, I'm not saying a ruler, a straight edge, like carpenters, and cutting a segment congruent to G itself, doing the same thing for the other one. This way, you will get 3 of the vertices of the parallelogram. And you know the parallelogram would have the 4th vertex, satisfying a couple of conditions. The problem is given after students were introduced to the idea of locus. Therefore, the 4th vertex happens to be on the intersection of 2 loci. One would be a circle or an arc of a circle with center D and radius H, and the other one would be another arc with center B and radius G. And where the 2 intersect would be the point C that we're looking for, and this is it. The look back, I think, you know, is this the only parallelogram we get? The answer is no, because it always depends on, in this case, it depends on where you drew your 3 vertices. Is this the only way of doing it? I'll leave that for you. You notice here that from the book, at the end, we put a reflect, which is connected to the look back. Students need to discuss and see if they can come up with something else. Now, to encourage the problem-solving approach, I can share with you another example, another thing that I actually did over the years. Students are afraid of exams. I mean, who isn't afraid of exams and so on? And they end up taking a test or taking an exam, not doing so well because it was not their day, they were not prepared, they made some mistake that is unexpected and so on. So I thought I can take that opportunity to actually have them develop their problem-solving rubrics a little bit more. This is a test correction sheet that I always gave, and I use this for not only one time, so that you really get the idea that it was very helpful in helping me help the students develop the problem-solving rubrics for themselves, etc. I use it for at least, to be on the safe side, 15 years, the last 15 years of my career. And when I marked tests, the normal tests that I've given to students, when I saw a problem and there's a mistake, usually, you know, we have the habit of circling where the mistake is. No, I didn't do that. I just marked the question as either wrong or partly wrong, and I didn't give the whole credit. And then I gave the test back to the students, and I gave them test correction sheets, which they had blank copies of afterwards, etc., where I asked them first to analyze the error, look at where you made the mistake. This means that see where you didn't understand the problem. Was it in the understanding the problem itself, or was it in making your plan or carrying out the plan, which is used to be most of the cases, etc. And then they had to present you with the correct solution. And notice here what I asked for specifically. This is an explanation that was given to the students, that they had to follow the POLIA steps. Understand the problem, develop a plan or make a plan, map that we call it now, carry out the plan, and look back. In each question, they have to do it this way, otherwise I will not be giving the credit back. And how much credit I give back, it really depended on how serious the mistake the student made and how good their explanation of the error was. And I gave up to 50 or 60% back of the grade. That means that the number of failures in my class went down. Does that mean that I actually inflated the grades? Believe me, if I compare the records, you'll see that. The only place where the curve of any test was changed was the lower end only, is that there were less than Fs, because you can consider yourself getting 40% on a test. If you manage to get 50% back, this means that your grade would become 70. So rather than having a disaster, okay, rather than having an F in the US system, you'll be having a C- instead. And that really proved to be very helpful. I used it at both levels, the high school level and the university level. I can send it to anyone that is interested. You could develop your own too. There are plenty of colleagues that develop their own form afterwards. So now we come to the next step. If you have any questions, you can interrupt about the problem solving. The second thing that I just wanted to tell you is about the approach that we took, and that would be that we allow the students to explore first the idea, and then we explain what we want to explain. And this is an early type of exploration, as you noticed from chapter 7, which I think of book 2, where we wanted to introduce, to be honest, I forgot whether supplementary angles or vertically opposite angles. And the only thing that the students are given would be this angle with measure of 80 degrees. And the student has to look and make their observation. The process that we follow in the exploration, or that we suggest to anyone that uses this approach, would be that such an activity to be given in class within groups. If a group is made up of 4 students, etc., let them first look at each of the problem individually and see what they can come up with it. And then when you notice as a teacher, by circling around, this is the group work also, that your students have finished their discussions, etc., you can tell them, or finish their work, I'm sorry, to turn around and talk about it themselves. And in the end, the group has to come up with a list of suggestions, which means that with the group work, doing the explorations, etc., you stop dealing with individual students. You are actually working with the groups themselves. After working together, each group would have developed their own list of observations, like the angle EFB would be equal to 100 degrees, the other angle BFG would be 80, etc., etc. And that will, to make sure that any activity is finalized in class and so on, then you'll have the groups discuss it among themselves, which means that you choose a group to give their opinion, and then you can ask the other groups to criticize if they don't agree with it. If they agree with it and they have a different explanation, then they can also contribute it to the class discussion. And then you move on to either an investigation or a problem-solving situation itself. Having said this, there are many students that could actually make a mistake. And this is your opportunity to make use of the mistakes. The recent research in how people think, etc., that every mistake will actually create a signal in the brain that is a learning opportunity for you, which means that if you find somebody making a mistake, try to see why that student made the mistake. Don't actually expose them like that, but just ask, why did you make this mistake? What did you think about it, etc. But be encouraging in asking this question. Have I done that? Yes. Did it work? Yes. Especially in the group itself, when you talk about it, those that make mistakes within the group, having been with the group for some time, will make them so familiar with each other, they feel like friends and so on. They are not really shy to face a whole class in the end, etc. Therefore, they will be encouraged to talk about mistakes and accept other people's opinion about it, etc. And when you deal with the group work, etc., it is better to address the groups rather than the individual students, which means that if somebody in the group has any question about anything that went on in class, they have first to deal with the group, and then the group asks the question, because if it can be answered within the group itself, then that would be much better. This is what you'll be looking forward to.
Ibrahim, we've got about 10 minutes left. There's a couple of questions that have come in. Do you want me to read them out to you now?
Yeah, just give me 2 minutes to finalize the group work that I'm. In terms of the groups that I'm suggesting, is that you establish an atmosphere for groups in class where you set it up with, I mean, there are so many different theories about group work, etc. The one I prefer would be that it should be a heterogeneous group, which means it has the different abilities in the class. The ideal, of course, it depends on the class size, etc. Size of the group would be 4 people. And the duration or the life of each group would be from a month and over, because they have to get used to working together, etc. And feel comfortable asking questions, answering questions, making mistakes in front of the other members of the group, and so on. Then afterwards, you can change the groups so that by the end of the year, you'll have almost everyone in class working with everyone else. In groups, there's a danger, if the question could come to your mind, that somebody dominates the discussion. This is something that you definitely should not allow. How can you kind of stopping this thing from happening? You assign different tasks that change on weekly basis, etc. There would be a manager of the group, there would be a speaker for the group, there would be the secretary, the person that takes notes, and so on. And this way, when you have anything to discuss with the group, you'll only discuss it with the speaker of the group, etc. Well, anyway, this is briefly saying what we have. If you want a more detailed discussion, read the introduction. This looks like an advertisement for the CSS. For each book, we developed a guide, instructor's guide, a teacher's guide that comes with it, and the introduction explains everything and puts references for you too. Okay, ready for the questions.
Thanks, Ibrahim. So the first one came in when you were showing us the previous example from the book. So the question is, how useful do you think constructions are in moving from a concrete understanding of a geometric idea to an abstract one?
Can you say that again, please?
How useful do you think constructions are in moving from a concrete understanding of a geometric idea to an abstract one?
This is only an application of one of the concepts in terms of the geometry. Like this is an application of the locus and so on. Given problems afterwards, this is only one thing, as I said. We have included investigations that will also encourage students to go a further step. The second thing that I mentioned is that, yes, of course, we want the students to explore first, and then they can be told. And definitely, you will see that after an exploration, after a discussion, somewhere later in the chapter, the abstract idea that we want will also be presented. I hope I answered the question, or I understood the question.
Okay, thank you. So the next question is, what do you think about the argument that problem solving may increase unnecessary cognitive load when introduced too early? They believe that showing worked examples are a more efficient approach. And then when learners become more proficient, then you introduce problem solving. When do you think it's appropriate to introduce problem solving?
Well, you may not really like my answer, but we introduce problem solving right from the beginning, MYP 1. And the chapter 2, I think, of that book introduces the problem solving procedure. The problem solving does not have to start with very advanced problems that the students may not be able to handle, but it is something that they really need to get used to. I mentioned the Van Heele husband and wife, etc. They wrote their dissertations in the 1950s of the last century and so on. And it was about geometric understanding and how this happens. And they put 5 stages of that learning. The first one would be exploration, which means that people, or if you're learning something, you just play with it till you discover some properties of it. I'll give you an example. Children have toys. And if you are really being careful in buying them the correct toys right from the beginning to have them learn about the geometric pictures and so on, there are boxes with different size on the box, and each side would have a square, a rectangle, a star, a circle, and so on. And they have objects that they fit it in with probably a hammer or not hammer. The first thing that the child really works with would be to just fit the correct figure in the correct shape that is in there. The next step would be to try to have the children know the names of these things. This is a square, this is a rectangle, this is a circle, and so on. And then it goes on to actually the concepts they're talking about, or the stages would be 5 stages, and the 5th stage would be the rigor. So check on the internet, you can also find it, the Van Heele model of geometric understanding.
Okay, this is not a question, it's a comment, but I liked it, so I just wanted to read it out. So somebody said about the kind of approach in general, this looks fantastic. It's like scientific method where we assume that knowledge is always provisional and open to evolve, even to a paradigm shift. So I just thought that was a nice comment. Somebody's asking if you could share the name of the book by Pierre Van Heele.
Unfortunately, Dina Van Heele, the wife, is the how can I say it? I'll say smarter than her husband, Pierre. She died shortly after she wrote her dissertation, so she didn't manage to write anything other than her dissertation. But her theory is well explained by different sources. As I said, you can find it on the internet. Her husband carried on the work. His name is Pierre Van Hele, and the book he mentioned. One second, it's something about insight and so on. Yeah, A Theory of Mathematical Education, Structure and Insight. It's relatively old now. It's from Academic Press, 1986.
Thank you.
So,
thanks, Ibrahim. I think we probably have time for one more. So how do model methods help students to understand and plan for their solutions in solving word problems?
Sorry, can you repeat that? As you noticed, my headphones are not really doing well. Yeah.
So I'm not sure if there might be a typo in the question, but it says how bar model methods help students to understand and plan for their solutions in solving word problems.
You know, the word problems would be just an application of a mathematical concept. The old concept of problems used to be only word problems, but word problems don't have to be only the word problems in that classical view. They could be any problems, even mathematical ones and so on. So as a word problem appears and a student is faced with it, the basic 2 steps that are suggested by Polya are of extreme importance. They have to try to read it, reread it, explain it to somebody else. And as Einstein said, if they cannot explain it simply, then they don't understand it till they end up being able to make a plan. So I hope that this addresses the issue that is raised.
Thank you, Ibrahim. I think we're going to have to wrap up now. So thank you, everybody, for joining. Thank you for your questions, and thank you to Ibrahim for presenting. There will be a follow-up email with the link to the recording and our email address. So if you have any questions that we didn't get to, then you'll be able to let us know. I can pass them on to Ibrahim.
I'm just showing also my.
Oh, yeah.
I'm also showing my email in case somebody wants to get in touch.
Perfect. Thank you very much, everybody, and thank you, Ibrahim, and enjoy the rest of your days, everybody.
Thank you.